So let's go through our bridge first. Hopefully you recognized that these first two problems on the bridge, these are the problems, these are the two reactions from last Friday. So these are the alpha alkylations where you added LDA and then an electrophile in the second step. Question number two is the two new reactions for today. This is the aldol condensation and this is the Claisen condensation. So I did go through the bridge assignments this morning and went through and X'd a lot of things and put some check marks in there. But for the most part, again, you don't get graded for getting things correct on your bridge assignment. I just want people to try. But please do be very critical of what you did wrong and try to fix it. If you can't figure out what, shoot me an email or something like that, or ask today. We've got an hour, and really we only have 4 reactions for this quiz. So I guarantee you all 4 of these reactions are going to be on there. So you need to know how to do all of them. But I'll give you the best hints that I can to get through all of them. All right, so let's start with that first step first, because for every single one of these reactions, you are going to be adding a strong base as your first step. Whether it is the first step mechanistically or the first, or like these lower ones, it's the only step. The first reaction is going to be the same. A base pulls a hydrogen off of one of these alpha carbons, the carbons next to a carbonyl. Going back to last outcome, the most acidic CHs are CHs next to carbonyls. And so that's why we can do this. That's why we can add these bases and pull the hydrogens off. All right, so LDA, we talked through on Friday as well that LDA is really, 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 really strong and also very bulky. So it is going to grab the first and easiest hydrogen it can grab, still has to be from an alpha carbon, but it never goes backwards. So it is not choosy. Sodium hydroxide, or this sodium ethoxide, on the other hand, go back and forth. So they will end up pulling off a hydrogen from a different alpha carbon. Anybody remember, given a choice of alpha carbons, which one will LDA pull a hydrogen off of or extract a hydrogen from? The left, why? It's easier, yes. So the most accessible spot, given a choice, is where LDA will pull a hydrogen off of. So this reaction right here, for the first step, is identical to this one right here. So we would pull a hydrogen off of the left side because it is most accessible. So either write that down or remember it or figure it out every single time. But this big, bulky, super strong base, LDA, is always what we will use in the first step of alpha alkylation. And it will always pull a hydrogen off of, if given the choice, the less crowded side, the less crowded alpha carbon. But still, always an alpha carbon, always a CH next to a carbon. All right, so in those cases, I know I'm kind of going back and forth a little bit, but I want to compare and contrast these first steps for all of these guys. You would get a C minus still at that same alpha carbon, but it would be the one on the left. Same thing for the second question, I guess 1B as it were. You're going to get that C minus and the alpha carbon to the left. So there are still 2 alpha carbons, but that's the one where we'll get. This turns your CH into your C minus, which becomes a nucleophile. And that's what we've done. We've changed the reactivity. You started off an electrophile and turned it into a nucleophile. All right, also remember from Friday, N minus is so strong that these reactions do not go backwards with LDA. So you will have converted 100% of your starting material into product. So the way that these differentiate from our new ones today is that on Friday, when you used LDA, you have no leftover ketone and no leftover aldehyde. So these should look a lot more like the way we've thought about these reactions in the past, as you start with almost like 1 molecule of this, you turn it into that, et cetera, et cetera. That's going to be really different from these guys down here. So first off, the location will be different. Sodium hydroxide, which is OH minus, is a strong base, but it's actually going to be unable to pull 100% of these hydrogens off. And it will do it on the interior or most substituted side of the carbonyls, the most crowded alpha carbon. So we would get a very different looking nucleophile. Your alpha carbon would instead be on the more interior side. Anybody remember why that is for this one? Why is this one more preferable? It's more stable. We did this at the end of class on Friday. If you don't remember, it's okay.
Is it because we compared the pKa of?
So the pKa is what tells you that this reaction actually goes forward only less than 1% of the time. It's the resonance structure, which would be a di-substituted alkene. That's the reason that this one ends up as the favorable product. For the ones above, the resonance structure would be a mono-substituted alkene. The alkene largely dictates the stability here because of the fact that the alkene is the major or most stable product because O- is more stable than C-. So that's stuff from Friday. Down here, given the choice, it kind of goes back and forth and back and forth. Think of this hydroxide as being a selective shopper that will try pulling off that hydrogen and try pulling off the hydrogen for both alphas, but finding at the end of the day that it's a more stable product if you end up with the interior or more substituted side with a negative charge, which ends up with a more substituted resonance alkene. Alkenes are more stable with more carbons attached. All right, probably you just want to remember that. The LDA pulls the hydrogen off of the less substituted alpha carbon, and sodium hydroxide or sodium ethoxide or any of those O- are going to pull the hydrogen off of the more substituted alpha carbon. But that's the reason why. All right, so for aldol condensation, this reaction goes forward about less than 1% of the time. So imagine I started off with 100 of these in my flask. All right, so there's not just one molecule, but 100 of these molecules. If you add sodium hydroxide, you might get one of these nucleophiles, which means that you have 99 of these electrophiles hanging around. So in the aldol condensation or this Claisen condensation, when you add these weaker bases, hydroxide is still strong, but relatively weaker bases, you are going to get only a little bit of nucleophile. You still have a lot of electrophile hanging around. And so we don't have a second step where you add your electrophile. They will instead just go back and react with another one of this molecule. So in these cases, a lot of times what I want you to think about is you'll always have excess of this hanging around. And so it ends up not reacting with itself, but reacting with another molecule of the same identity. All right, which alpha carbon, this is kind of a trick question, which alpha carbon will you deprotonate down here? Yeah, the only one that you have, that's the one on the left. All right, this is really important. I had a couple different folks try to pull a hydrogen off of that spot right there. That is not an alpha carbon. Alpha is only right next door to the carbon. Right? And the reason you can pull a hydrogen off of the alpha carbon is that that C- will have resonance to the double bond O. Nowhere else in a molecule will you have the resonance to the double bond O unless you're right next to it. So the only alpha carbon is this one right here. I'm actually going to erase that arrow. Don't do that. And so the sodium hydroxide, well, this is sodium ethoxide. It's an O-, 2 carbons. It's going to react just like ethoxide or hydroxide. It's just an O-. That's the most important part. And you would have that C- right there, just because that's the only one. So with the Claisen condensation, it's the only one where you start with an ester. All of those other reactions, you start with a ketone or an aldehyde. But when you start with the ester, you only have one alpha. You can only have one alpha. And so there's no choice to be made. That's the nucleophile. All right, so we have in all of these cases done the first step, and it's identical-ish in all of these reactions in that the base pulls a hydrogen off of an alpha carbon and gives you a C-, which is a nucleophile. What do nucleophiles react with? Right. So in this case, again, with LDA, we push it 100% forward. We have none of this thing left over. So it has to sit there and wait for you to add an electrophile. All right, so here we go. We have our nucleophile. I'm going to number the carbons. 3, 4, 5. 5 carbons in blue. All right, our electrophile is this alkyl halide right here. Zoom in a little bit. And that has 5 more carbons, but I'm going to give them different numbers, 6, 7, 8, 9, 10. Carbon blue 1, which is our alpha carbon that we just made into a C-, that's my nucleophile. Which carbon's your electrophile, Olivia?
Number 2.
Okay, so that can't be your electrophile because they're conjoined to each other and there'll be resonance. So that carbon right there is actually going to be smoothed out through resonance. So this is not simultaneously a nucleophile electrophile. You need to have an electrophile from another molecule.
So, alcohol.
Right, perfect. So your alkyl halide will be your electrophile, and specifically, which carbon is your electrophile? Yes, the one with the leaving group, so number 10. As a reminder, there are only really 2 electrophiles that we have covered in this class. Carbon with a leaving group, like an alkyl halide, and a C double bond O. That's it. All right, so your nucleophile, which is blue 1, is going to attack your electrophile, which is green 10, and kick the bromine off. The bromine will be gone. So when you draw the product of this, I would recommend that you draw the nucleophile exactly how it is with the same spatial orientation, just to avoid messing yourself up, and number it the same way you did. 1, 2, 3, 4, 5. And then we should have 5 more carbons attached to number 1. So 1, 2, 3, 4, 5. It's very easy to get the wrong number of carbons here. So please take the time to just write those numbers. Just for the sake of correctness, we attached number 1 to number 10. And I should still have 9, 8, 7, 6. So now I have all of my carbons and I've got the right product. So this chunk over here came from your electrophile. So notice that what we have done is just attached an alkyl chain at one of our alpha carbons. And there is no bromine left over. The bromine is not attached anymore. The whole point of the bromine was to be a leaving group, which is what made that carbon an electrophile in the first place. You kicked it off. So sure, Br minus is sitting around here somewhere, but it's not attached anymore to anything. All right, so that's a reaction from Friday. Any questions on that one? The second one is very similar in that you have the same nucleophile. It's different in that you have a different electrophile. I'm going to number my carbons in my nucleophile the same way. 1, 2, 3, 4, 5. And then I've got 2 carbons in my electrophile here, so I'm just going to number those 6 and 7. It doesn't matter which one you write 6 and 7. These are just your numbers for keeping track. All right, so Savannah, which is my nucleophile? Yeah, that carbon number 1 right here, same one as above. And what's my electrophile?
I did it, I used it as like carbon number 6, but
yes.
You said you don't want those, or is
it is 6. So the carbonyl is the electrophile. So the number 6 is what should be attached. Ooh, so that's the carbon you attach. And then electrons go where? To the O, correct. So when you have this attached in the product, I'm going to redraw my nucleophile exactly the same way. 1, 2, 3, 4, 5. Go ahead and number it before I do anything else. 4, 5. So carbon number, I'll have 2 carbons attached to number 1. So boop, boop. And I'm going to go ahead and number these. Which one did you say we make the bond to? 6. So this first one here should be 6. That one will be 7. Which one had the oxygen? 6. So which one still has the oxygen? Yes. So I got a lot of different answers for this one right here, which is, okay, does it make sense now? If you got that right the first time, awesome. If you didn't, it's okay. The idea is just to make sure that you attached it at the right place. So number 1 had to have been your nucleophile. And number 6 had to be your electrophile that still had the oxygen attached. So this last step with a little bit of acid, hopefully we only add a tiny bit of acid, otherwise some bad things can happen here, but we'll turn our O minus into what? Yeah. Does that make sense? Did you have that one right in the bridge? I don't remember. Oh, gotcha. Yeah, so if you turned it in by like 10, 20, I graded them this morning. If not, I'll get to them after class today. But I'll make sure to go through, hopefully from class today, you'll get the idea on what to do. But just make sure that you know, if you made mistakes, make sure you know why. All right, so that's all of our carbons. That's all of our stuff attached together. The big difference between these first two reactions is that we added a slightly different electrophile, and so we have slightly different stuff left over. If you ever attack an alkyl halide, you kick off the halogen, and you just have the alkyl group. If you attack a ketone or an aldehyde, then you will have an oxygen left over because you don't kick off the oxygen completely. You just go from double bond to O down to single bond. All right, questions on those guys? That's Friday stuff. Feel pretty good about that? Pretty good, Olivia? Pretty good, pretty good, okay. All right, I am going to show you a little bit of how this one is gonna go, but the whole video on aldol condensation is still there if you need to go back to it. And then I'm gonna show you really how I shorthand this. This is a long mechanism, and I don't think that going through the entire mechanism is a good use of your time, partially because the more steps you go through, the more times you have to make a mistake, and the more likely you are to make a little mistake that ends up compounding. So even when I do aldol condensations, I just like to kind of look from the end backwards. So that's what I'm going to show you how to do here. All right, so first off, this is your alpha carbon and this is your nucleophile, correct? Where's your electrophile? So this is these two are a little weirder in that you don't add another electrophile. Sodium hydroxide certainly is not your electrophile. It's an unreacted starting material that's your electrophile. So think of this like we had 100 of these molecules in a pot, and I added sodium hydroxide. It's going to turn one of those 100 molecules into a nucleophile, but then you're going to have 99 left over as electrophiles. So you don't need to add another electrophile. You just have more of this thing hanging around waiting to be your electrophile. So your electrophile will just be another molecule of that thing. And these will react together. It ends up being really similar to this reaction, where you started off with a ketone or aldehyde, made it all into a nucleophile, but then you added more carbonyl in the second step to be your electrophile. Well, in the aldol condensation, you don't add any more carbonyl to be your electrophile. It's the same electrophile that you had in the first place. We just only turned a little bit into a nucleophile, so we had a bunch of electrophile left over. So think of it as reacting with another molecule of itself. We could go through these steps, and what would happen is your nucleophile would attack your electrophile. So we're just going to label these real quick. That's C- right there, your alpha carbon, that's your nucleophile. Where's your electrophile? Yep, the carbonyl of another identical molecule. It is identical in the carbon shape, but notice that this is one of the ones that wasn't converted into a C-. So it's the same thing, it's just neutral instead of a C-. So in the aldol condensation, anybody remember what you end up with at the end of the day? This is where we're going to kind of shorthand this a little bit. All right, I'm going to walk through this, but we're going to erase all of this and go back to it and simplify it. All right, so your nucleophile attacks your electrophile, just like we did above, which kicks up the electrons to the oxygen, and then we're going to protonate it. I'm going to skip that step. It's going to happen. And you would have this. So we're going to join on our nucleophile to our electrophile. I'm going to number these carbons just for the sake of making sure I'm good. I'll number them the exact same way that we did before. So here's my nucleophile. Carbon number 3 is my nucleophile instead of number 1. Remember, when you add ethoxide or hydroxide, you end up pulling the hydrogen off of the most substituted alpha carbon. So now we have another molecule. I'm going to number it the same way, just in green. It's still that same 5 carbon chunk, 1, 2, 3, 4, 5. So my product, I'm still going to have those 5 carbons. 1, 2, 3, 4. So it's green, 5 of them, blue, 5 of them. The 5 in blue were from my nucleophile. Number 3 was the reactive site that made the new bond. For my unreacted or leftover ketone, I numbered it the same way, 1, 2, 3, 4, 5, but green 2 was your electrophile. So blue 3 and green 2 made a new bond, and that's what we've got right there. Whew. Okay. So the difference between this reaction and the one above is that this one went stepwise. And these little 1, little 2, little 3, you're thinking about this practically in lab. What you do is you put together your starting material plus little 1, you do the reaction, and then you do your purification. We've done purification a bunch of times. You extract with, you do some liquid extraction, recrystallization, something like that. But you clean it up and you don't have any leftover base at that point. You just have this. And then you go ahead and add the second thing, let it react, work it up, take it out, clean it up, and then you add something else. Down here, there are no steps. You're just adding hydroxide and it's all just going. And so you still have hydroxide hanging around when you get here, because you might get here in like 2 seconds. You haven't had the time to take out the hydroxide. So you still have hydroxide, which is still a base. And you still have an alpha carbon, which is still acidic. And so your base is still hanging around and you can't stop this in between. So what it will do is the same base in the same pot, moments later, will pull a hydrogen off of that alpha carbon and make a C- here. So all of this is probably in your notes because you went through and watched the aldol condensation already. This is the same thing. So you can write it down again if you want to, but I'm far more interested in you kind of following this story. So now we have a C-, which is going to have the ability to shift up here, making a C double bond C, pushing those electrons up to the O. And this would make an enolate. This is just the normal resonance structure. So think about this as we turn a C- into an O-, but it's resonance. So what happens then? Yeah, but it just kind of goes back and forth, right? It doesn't really go back and forth. It's just kind of some combination of the two, but just think it goes back and forth. O-, back to a C-, O-, back to a C-, O-. What's more stable? O-, but then back to a C-, and O-, and it just goes back and forth. So it's going to go up and down and up and down and up and down, but it doesn't really matter, right? It doesn't get you anywhere. All right. Well, in this specific case, it's actually got a choice. Alternatively, it could come down here and break that bond. This should look very similar to resonance, but in resonance, you don't break anything off of your molecule. So what happens if I go this way? Yeah, perfect. It creates a C double bond C, just like it did in resonance. But in this case, you're breaking off a single bond. Who gets the negative charge after this is all said and done? Who are we kicking off? Yeah, the O. So either way you go, you're turning your C- into an O-. But if you go up, you just come back down again. If you go down this way towards the alcohol and kick off the alcohol, you're getting an O-, but it's pretty much done. And you're making more molecules, which is more stable. And it's much harder for that thing to come on in here. All right. Don't write this down because it's probably going to be a little bit overcomplicating, but I do want to let you know these reactions are reversible. So in this reaction, notice that what we have here is a ketone and then that alpha beta. So this is an enone. You might remember enones where fiercely strong nucleophiles can attack the carbonyl, but relatively weaker nucleophiles will attack that beta spot. And it can attack that beta spot. This is actually the backwards reaction of this we did in outcome 5, but it would just go backwards to this thing. And so this reaction in reverse is actually something we did already a couple of weeks ago. But suffice to say, it's mostly going to end up as your product here. And this is what we will get. And I'm going to number those carbons. 1, 2, 3, 4, 5. And blue. 1, 2, 3, 4, 5. So notice that at the end of the day, what we have made is an alkene. We started with a C double bond O on carbon number 2, and our alpha was to carbon number blue 3 here, and we made a new double bond in between them. And so in the aldol condensation, what we've ended up kicking off is OH and H, which is water. And so we call this a condensation because you're basically making water kind of out of nowhere. All right, so that's a lot of details. I'm going to erase most of this, except for I'm going to leave that product right there. And I'm going to show you the way that I think about these things to try to make them oversimplified. I love mechanisms, and I think mechanisms are absolutely worth doing. In fact, to me, if you draw these mechanisms in kind of step 1 and step 2, you're far more likely to get it right because you're just kind of following who joins whom. But in this case, there's so many steps that I approach it a slightly different way. All right, I'm going to take this for granted, but here we go. When we do the aldol condensation, which we know that we're doing because we're starting with a ketone or an aldehyde, and we're adding just hydroxide base, we're going to end up making a brand new carbon-carbon double bond between the alpha carbon of one molecule and the carbonyl of another. And so the C double bond O of one, you line up with the alpha of the other, and then you just squish them together. And so the product ends up looking like one of these is left exactly how it was, but the alpha made that new bond. And then the other one looks exactly how it did, except for instead of a double bond O, it's a double bond to that alpha carbon of the first one. So I skipped a whole bunch of steps, but notice that I turned a C double bond O, which is my electrophile, and my alpha, which was my nucleophile, into a brand new double bond. I skipped all those steps, but I sandwiched them together and made a double bond. And notice that what I just did, I ended up with the exact same product as when I went through all those steps. You get a brand new double bond in between. And so that's how the aldol condensation goes. And kind of by minimizing the number of steps that you're doing, you can just kind of sandwich those things together and be done with it. And that's how it works. Questions on that? So let's do another example, kind of shorthanding it. I'm going to erase all of this unless anybody has any questions here. You're running out of time for questions. No, let's go on. All right, so let's start with, let's say that I start with this aldehyde right here. And I just add sodium hydroxide. So where's your alpha carbon? To the right. It's the only alpha carbon you have, so you don't need to decide. So this is your alpha carbon right here. It's number 2. And then below that, draw the exact same molecule, but just aim that C double bond O towards your alpha carbon. Then to make your product, turn the alpha and the carbonyl into a brand new alkene. I'll redraw my nucleophile because that really hasn't changed very much. Carbon number 2, I will now have a C double bond C to what was your carbonyl in the second molecule that you drew. So all of this part here came from your one, it's kind of the back carbon backbone of one part. And then the top part is all just the carbon backbone of the nucleophile. Kind of have the same molecule sandwiched together. How's that feel? Hopefully easier, simple, maybe not easier, but simpler. So that's the best way, I think, to approach the aldol condensation, is to kind of, as much as it hurts my heart, skip the mechanism, put them together. That's how it works. All right, questions on that one? So if you go through the mechanism of this one, which you don't have to do, it's the same as the alpha alkylation we did on Friday. It just goes one step farther and puts a double bond right here. All right, so let's go down to the Claisen condensation. Claisen condensation isn't really a condensation because you don't make water, but it's called that anyway. Let me clean this up a little bit, so it doesn't look like I've got carbon sticking in the space. All right. So I have a nucleophile, and another molecule of this is going to be our electrophile. So you kind of just want to draw that molecule again. But when you do so, it's really helpful to put your electrophile of this molecule next to the nucleophile we just made. Here's my nucleophile, my C minus. If I were to draw another one of these molecules, where's your electrophile on an ester? Which C? Yeah, the C double bond O. So it's still that carbonyl. I'm going to try to draw this one a little bit sideways here. So I've got all of my stuff. It's worth numbering your carbons, although there's not very many that actually matter. Here's your nucleophile. It's kind of the carbon number 1 of this little 2 carbon chunk. Nothing's happening over here. For my new molecule that I'm adding in, maybe here's my number 1, here's my number 2. So this is your electrophile. This is your nucleophile. So your nucleophile is going to attack your electrophile. All right, so Sydney, tell me what's going to happen when you attack an ester.
It's going to shoot up to the O and then shoot back down and kick off that.
Yep. So in an ester, if you ever attack the carbonyl, you end up kicking off the O whatever that's attached. All right, so once again, let's go ahead and draw our nucleophile the same way it was, because your nucleophile does not change very much. It just ends up with something new attached. So how many carbons have I added on to your carbon number 1 when you attacked this chunk? Yeah, 2 more carbons. It's in green, the 1 and the 2. So let's go ahead and draw 2 new carbons there. Which one did I attack? 1 or 2? 2. So that should be number 2, and that should be number 1. So let's check for our functional group. When I attacked this, it was a carbonyl. And then Olivia, you kicked electrons up to the O, and then they came back down, right? So what is the functional group now? Yeah, it's still a carbonyl, right? It's technically now going to be a ketone, but it was a carbonyl. You kicked electrons up, making it a single bond O minus, but then they came back down, and so it should still be in the product a double bond O. So this chunk right here came from the carbonyl of your ester. And notice that that's this part right here, but all of that was your leaving group, so it all got kicked off. So the Claisen condensation to me is a lot simpler than the aldol condensation, because it's really 2 steps. Pull the hydrogen off of the alpha carbon, like we've done a whole bunch of times, every step, every reaction this week. And then your nucleophile of 1 attacks the carbonyl of draw the same molecule again. And then it does the slingshot mechanism that we've seen a couple weeks ago, same thing. And then you just make sure to number your carbons and have them attached in the right place. So this is not simple. This is not something intuitive and easy, but if you practice it, you see that it'll get really repetitive. This is always what happens in the Claisen condensation. All right, I'm gonna pause here and give you some details. This is the right answer. Everybody good with that? All right, we have to be aware that there is a second step of this reaction where you add acid. And as you look at this, it shouldn't matter. But much like the reaction above, when we went through the mechanism of this one, the reason that it kept going and ended up with that double bond is because I still had a base hanging around. Well, this one also still has that base hanging around. It's an O minus. And so once you get this product, there's this 1 carbon in between that is still an alpha carbon, but now in the product of this Claisen condensation, it's alpha to both of them. So to pull a hydrogen off of there is even easier because the C- is even more stable because it has resonance to even more oxygens, making even more possible O-. So this hydrogen right here actually has a pKa closer to about 5, which is like a carboxylic acid. But the reason why is because a C- there would have resonance to 2 different O-, just like a carboxylic acid. Its product has resonance between 2 different O-. So this is almost as acidic as a carboxylic acid. And certainly, if you had an O- in there, you're going to pull that hydrogen off. You're going to turn this thing into that. And that is actually your end product of this reaction. But we don't want that to be our end product. We wanted it to be this thing. So we need to go backwards. Because the base pulled that hydrogen off, you want to put the hydrogen back on again, you just add acid. So that step 2 of adding an acid, it really just goes back to where you were when you got to where you wanted to go. So basically, Claisen condensation gets your product and then overshoots. And you got to back it up a little bit by adding acid. So this is a little bit maybe of an afterthought. I want to point out that it's true, but really that's the product. You were done at that point. You just overshot and now you got to take it back again. Another thing we need to be really aware of here is the identity of the base that you use. So notice that with the aldol condensation, we just usually add sodium hydroxide. But with the Claisen condensation, you can't do that. The reason why goes back to our reactions from a couple weeks ago. So this is also going to be extra information that you may not need, but I just want you to be aware of it. If you added OH minus, OH minus reacts in 2 different ways. O minuses are what? Base and nucleophile. So we want it to act like a base, but it also can act like a nucleophile. So there are competing side reactions that will happen here, and you don't get to decide because it both wants to be a base and a nucleophile and it doesn't care. So you don't have to write these down. These are just more precautionary tales than anything else. Your O minus can attack that carbonyl because it's an electrophile, kick electrons up to the O, come back down, and kick this off. And in which case it would replace this O with 2 carbons with an OH. And it would change your ester into a carboxylic acid. And then it's not an ester anymore, and then you're not going to get that product in. So instead, we use that O with 2 carbons attached. So this is what we used as our base. Well, what if this is still a nucleophile? What happens if this attacks? What does it replace this OCH2CH3 of with? What is this? Maybe I messed you up when I changed the color. So if we added hydroxide, it could kick off your leaving group, which is an O with 2 carbons. And if we added hydroxide, it would replace this O with 2 carbons with an OH. But if I added this base instead, which is also a nucleophile, if it acted like a base, great, I'm going to go forward with my reaction. What if it acts like a nucleophile? Well, it can do this. Boop, boop. But in that case, it would replace this leaving group, which is an oxygen with 2 carbons, with this nucleophile, which is what? Oxygen with 2 carbons. So this will happen, but it doesn't matter because it's replacing the same thing with the same thing. So we always match our base with our leaving group so that there is no problem with a side reaction. It's pretty nifty. Furthermore, if you ever use ethoxide, you need to use ethanol as your solvent because this O minus can pull off the hydrogen here and it can actually react with your solvent. But if that O minus pulls off a hydrogen and becomes OH and turns your ethanol solvent into an O minus, you get the exact same things. Therefore, that will happen, but it doesn't matter. If we did this in water, you would get an O minus, and then you'd go through all of those same problems. So we need to match three things up in our Claisen condensation. We need to match the esters leaving group with our base, which is just the O minus, which our solvent, which is the same thing, only with an OH instead. So for you guys, I'm going to give you the reagents where they're all going to match, but just be aware we have to make sure those things match up, or else crazy. I'm not going to give you a trick question where they give you different all kinds of combinations, but that's why we use this base. That's why we don't just add hydroxide for all of these, because of issues that could occur. All right, questions on any of this? I know we've kind of gone slowly through here. I hope it was worthwhile because it is these 4 reactions. You just need to know way fewer reactions than a couple of weeks ago, but you need to know more deeply and they're more complicated. All right, so let's make a whiteboard. At the end of the video for the Claisen condensation, there was a problem that I asked you to try, and so I said we'd go through it in class. So we've got to go ahead and go through that one in class right now. It looks like this. NaOCH3. By the way, the solvent here would have to be methanol. I didn't write that down, but that's fine. And then lastly, you add an H+. All right, so you guys hopefully can recognize the Claisen condensation. It's the only one we have that starts with esters. All right, so in the first step, my O minus is going to pull a hydrogen off of where?
Carbon on the left between the benzene.
Yeah, the only alpha carbon, the alpha carbon we have, which is this one. All right, so if it's okay with you, I'm going to shorthand that. That C is going to turn into a C minus. Everybody okay with that? Usually I highly recommend you don't skip steps, but this is acid base and the hydrogen drawn there is usually not drawn. So it's pretty easy to just turn that into a C minus with a lone pair. All right, what would this react with? What electrophile? Yeah, so we got to draw the same thing. So what we should do is draw this same molecule without the C minus and put our electrophile, which will be this carbon, carbonyl, near our alpha carbon. So I'm going to kind of turn this sideways. I highly recommend that you just move your paper around in whatever way is most convenient for you to get it close by. I kind of turned my iPad upside down to do that. But now I've lined up that there's my alpha carbon nucleophile and here's my carbonyl electrophile. So we can go ahead and have my nucleophile attack your electrophile. It kicks electrons up to the O, and then they come back down, and what do they kick off? Yeah, that OCH3. This is always the leaving group of an ester. It's your O and then whatever is attached. No, that's a little crowded. Oh, I can't zoom in on the whiteboard. So we're going to go ahead and draw out our nucleophile exactly how it was. And I'm going to have attached at that alpha carbon, there's going to be a carbonyl and then a CH2 and then benzene ring. So hopefully we are just checking the thing that you did at the end of the video, and hopefully that's what you got. It's easy to leave out carbons, so I highly recommend that you number carbons. I didn't do it here because hopefully you guys did this already, but that would be the product. Notice that the nucleophile up here is the same as the top of this product, and this kind of most of the electrophile minus the leaving group is the same chunk that I have there. And they're attached to what was the electrophile and the alpha that was the nucleophile. So all 4 of these reactions are attaching something new at your alpha carbon. All right, questions on that one? This gets really repetitive if you practice it. So hopefully there's a steep learning curve on these condensation reactions, but after you get it, and I've done it a couple of times, they get to be really repetitive and they're really the same thing every single time. All right, let's do one more of these. All right, I'm going to change that around a little bit. Use almost the same molecule. All right, so take about 3 minutes. Figure out what reaction this is and what product you're going to get. Don't forget that one's still attached. Great. So this is the aldol condensation, right? This is anytime you've got the O- as your base, you're going to end up reacting this molecule with itself. So if it's an ester, it's going to attack an ester. If it's a ketone or an aldehyde, it's going to attack a ketone or aldehyde. All right, which alpha is going to be deprotonated? 1 or 3? 1, why? More substitutes, the more crowded one, yes. So what we want to do is draw this same molecule again. I numbered it blue 1, 2, 3, and I'm going to number it green 1, 2, 3. But you want to be aiming your carbonyl of the electrophile you drew at the alpha of the nucleophile that you drew. And you are going to make brand new carbon-carbon double bond between those carbons right there. I'm going to redraw my nucleophile the same way that it was in my starting material. I'm going to number it the same way, 1, 2, 3. And then I will have at that alpha, carbon number 1, double bond to a sloppy benzene ring, but to our carbons, 1, 2, 3 there. Oh, 1, 2, 3. Is that what we got? Feel good about that? All right, so that's the aldol condensation. I hope that that feels like an easier way to accomplish it. All right, so in our last 10 minutes, let's think about doing these reactions backwards. So another part of your quiz will be, what's the reagent to add? And sometimes you got to be pretty creative, and sometimes you don't. When it comes to adding reagents, note that those first couple reactions on our bridge, we need to add a base first and then figure out the electrophile. But in the Claisen and the aldol condensation, all you add is the base. That's all you need to worry about. All right, so let's go through these. Sydney, good news, you get to go first. We have cyclopentanone. And in our product, what have we attached?
Just a long chain carbon.
Yes. And where has it been attached?
Side of the ring.
What do we call this carbon to the side of the carbonyl? Yes. So it's got to be at that alpha carbon. So as it exists right now, this alpha carbon is not reactive. So what do we need to add in the first step?
OH or base.
It needs to be a base. So if we added OH, we would do the aldol condensation, and one molecule of this would be attached to another cyclopentane. We don't have that. So what base do we need to add?
The Na.
No, it's the one from last Friday. 3 letters, starts with L.
Oh, LDA.
Right. So the LDA is the irreversible base that will turn all of this thing. We're going to kind of go sideways down here. Or LDA will make all of it into a C minus. And in that way, you don't have any leftover ketone, so it's not going to go back and react with the same molecule. Sound good? Okay. So now we need to figure out what electrophile in a second step would attach this 4-carbon chunk.
So, like a 4-carbon attached to a Br.
Perfect. And where should we put a bromine? The ends are in the middle somewhere. Yes. We want to attach it at the end carbon, so we need to have a leaving group on the end carbon. And that would be great. Your nucleophile attacks your electrophile is just SN2, and it would attach a 4-carbon chunk, and that's where you would have it. Perfect. Questions on that one? So it does take a little bit more, I think. It takes a bit to think through this, but whenever we're attaching something out at an alpha carbon, and for all of these, you're going to be attaching something at an alpha carbon. The first step needs to be a base, and the second step needs to be whatever you're attaching to it. All right, Olivia, good news. You get to start with the same starting material. Even better news, you get to have a different product.
So I need to start with the base first.
You do need to start with the base first. Oh, hold on, let me go ahead and finish this off. So this would be step 1, LDA, step 2, boop, 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 boop. All right, so what's your step 1?
NaOH.
All right, so if you were to add NaOH, you would turn your alpha carbon into a C minus in only a small fraction of your starting materials. And then you would have more cyclopentanone left over, and they would react with each other before you got to step 2. So if you wanted to have a cyclopentanone attached to the alpha carbon, then add sodium hydroxide. But we don't want that.
Don't want that.
Right.
So say that again, if you don't want.
So sodium hydroxide and the
Oh, it just does the
ethoxide,
same thing.
it reacts with itself, right? Not itself, but another identical molecule. And that will happen before you get to step 2. And so you don't get to choose your electrophile if you add sodium hydroxide. The only time you get to choose your electrophile is if you add LDA. Because LDA is such a strong base, it had the pKb of like -21, that it will turn all of your starting material into nucleophiles. Does that make sense?
Yeah.
Okay, so what should your base be in step number 1? Heck yeah. All right, so LDA will turn 100% of your cyclopentanone into an alpha carbon nucleophile. All right, so this is the chunk that you're attaching at your alpha carbon here. Your alpha carbon became a nucleophile, so what does your other chunk need to be? Electrophile, right. So don't peek, think about it. You're not gonna have anything to peek at in your quiz. You only have 2 different types of electrophiles. One is an alkyl halide, in which case you kick the halogen off and it's gone. So that's good if you just want to attach a halogen or an alkyl chunk. What's the other one? Nope, the other electrophile. I'll give you a hint, it's
Oh,
right
it's
here.
the double bond O.
A C double bond O, perfect. So you need to have a C double bond O. I'll spot you that. And this is what's going to happen. And it would end up with a single bond O left over, which is what we want. So what should be attached to this C double bond O to leave us
The
this
rest
chunk?
of
The rest of the stuff. Yeah, exactly. So, boop, boop, boop. And then over here would just be a hydrogen. Does that make sense? All right. This is really kind of a retrosynthesis-y kind of question. I don't know if that's a word, but you know what I mean. That kind of what do you attach together to end up with a product that you're shooting for?
So how do you know there is an H and it's not just something we can bond to the carbon?
Well, carbon needs to have 4 bonds in your starting material.
So I'm saying like why is it an H and not just a carbon?
If it was a carbon, then you'd have another carbon stuck there in the product. But in the product, that carbon right there has basically an isopropyl attached on one side, and it has nothing else attached. So therefore it needs to have, nothing else. It has a hydrogen. So it had to have had a hydrogen in the first place. But we don't have to draw our hydrogens when they're in line angle structures. So if you didn't draw that hydrogen, that won't need to draw. This would be fine, but you can't have more carbons attached or else they'd be attached to the product as well. All right, technically this would give you an O minus. And so what will we need to do after that? Yeah, just add an acid. So technically you would have a step 3. And this could be water or an acid. Any of those things would be fine. So these should look a lot like your bridge problems. LDA followed by an alkyl halide, LDA followed by a ketone or aldehyde, and then an H+. But we're just doing it backwards. All right, Savannah, you get the last one. You ready? Okay. Same starting material.
So it would be NaOH and
Yep, that's it, NaOH. And that's it. That's the only thing you need to add. So the Claisen or the aldol condensation, they're really hard going forward, I think. But figuring out what the reagent is, you just add that. It's a strong base, but it's not nearly as strong as LDA, but that's all you need to add. And then this guy will react with another identical molecule. And the alpha of one and the carbonyl of the other end up making their bond. So you don't need to draw the molecule again. All you need to say is sodium hydroxide. That's it.
So what would the Claisen look like?
All right, Claisen. So let's do, here, I'll attach a cyclopentanone because that's our pentane. That's our trend that we're doing right now, apparently. Boop, boop, bop, bop. Do, 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 do. So notice that I've got that same thing up here, and I've attached everything minus the leaving group at the alpha carbon. So what reagent do I need to add for this? Yeah, so you need to match up the O minus with something, but it's just an O minus. But you need to match it up with the leaving group here. Yeah, so it'd be the O minus with, in this case, like an isopropyl group. And so technically this is a step 1. And then step 2 is the acid that undoes it overshooting. I have never counted off if anyone forgets that step 2 of an acid. The main thing here is you need a base. That's it. So with aldol condensation, sodium hydroxide is fine. With the Claisen condensation, you need to add an O minus, but make sure that you match up whatever's attached to it with whatever is attached to the leaving group in the ester. All right, it is 2:01. I've officially kept you a minute late and I apologize for that. Any questions about these? So please practice them. till they get old. It's only 4 reactions, so you will have to do all 4 of those. Thank you very much. Have a lovely week. I will see you all on next Monday.